Okay, so welcome back to another video. So in today's video we have the following infinite sum, starting with our index at k is equal to 2 instead of the usual videos I made that starts with equal at k is equal 1 or 0, of 1 divided by 2 to the power k minus 2 multiplied with tangent of pi divided by 2 to the power k. Now I say that it's similar when although it really isn't, but what I'm saying similar is the fact that we have that a trigonometric function of the input has pi divided by 2 to the power k. Not too long ago I did a video where I actually did the improper integral of our product, our infinite product series of cosine of the same input. So just from judging from that, you can probably maybe guess that we're probably going to use a similar method on how to evaluate this infinite sum. And in a sense, yes, you are correct, but there's going to be a little bit of a manipulation there. And then really it's just all but just rewriting this, the sum itself, of course, but eventually we're actually getting to a point where we can actually write this in terms of a limit, using that to our advantage, and then eventually we'll get to our desired sum of the following infinite sum. So I don't have any other thing else to add to that, so let's actually just jump in. So we're going to start with the following partial product series. So here we have the partial product from k is equal to 1 of cosine of x divided by 2 to the power k. Okay, I did prove this value. We evaluate this back in the video I just mentioned, so if you want to check that video out, the link will be in the description below. So we know that if we actually just apply the double angle formula and then solve that work again, that's on that link for you to see, we get that the following has the closed form of sine of x and then divided by 2 to the power n, then multiply with sine of x divided by 2 to the power n, like so. How about we actually do something a little bit different and adjust this back such that we re-index this back to k is equal to 0. So when I say readjust the index, we're not really going to change our series that we're actually being multiplied to. So I know what you're thinking when I say readjust. Wouldn't that mean that not only would I change this back to 0, readjust to this series that we're fixing, but won't we have to do the same on the right hand side of the equality? No, that really won't do anything. If anything, that's just going to add more work to the mess, and we're not going to do that. Instead, we're actually going to do this a little bit differently. So I said that we're going to start that with k is equal to 0 for our index, but how do we get to there? How about first let's evaluate at k is equal to 0 first. So if I put k for 0, so this is x divided by 2 to the power 0, that's just 1, so x, cosine of x specifically. So and since this is a product, so it's just all about multiplicity. So it's just cosine of x, then multiply with our partial product series over here, k is equal to 1, cosine of x divided by 2 to the power k. So even though there's a cosine here, cosine of x here, that means I'll multiply cosine of x to the other side. So sine of x, then cosine of x divided by 2 to the power n, sine of x divided by 2 to the power n. Now, doing so, we can actually just readjust the left-hand side of our equality and write that as a new product or partial product series. This time, our index starting at k is equal to 0. So cosine of x divided by 2 to the power k. Where does this leave off with the right-hand side of the equation? Well, it doesn't look like it can simplify further from there, right? It actually can. So I did mention that you actually can use the double angle formula, and recall that it's sine of 2x is equal to 2 times sine of x then cosine of x. Guess what? There's a sine of x cosine of x. However, if we just multiply the 2, so in other words, multiply the 2 and divide the 2 for both sides, then I'll just rewrite 2 sine x cosine of x as sine of 2x for the numerator. And then I said that we will multiply and divide a 2, even though that changes the numerator, so that's fine. So if I divide a 2, then that means that changes our base here to add plus 1 to the exponent. So we have 2n plus 1 of sine of x divided by 2 to the power n. So that's good. That's what we got. So now from there, let's actually take the natural log of both sides. So now let's actually switch to the new marker. Let's start with purple. Now we take the natural log of both sides. So the partial product, k is equal to 0. Cosine of x divided by 2 to the power k is equal to the natural log of sine of 2x, then divided by 2 to the power n plus 1, then multiply with sine of x divided by 2 to the power n. But what you'll notice is that from the left-hand side, since we have the natural log of the product series, by using the definition of continuity, we can actually write this as a partial sum of the natural log of cosine of our input. So now here we have the input, our partial product k is equal to 0 of the natural log of cosine of x divided by 2 to the power k. And then we set this equal to, so using our rules of natural logs for the left hand or the right hand side, so here we have it's the input under the division, so it's subtraction natural logs. So we have the natural log of sine of 2x subtract with the natural log of 2 to the power n plus 1, then subtract with the natural log of sine of x divided by 2 to the power n. So now let's actually take the derivative of both sides of the equation of our equality in respect to x. So here, I'm just going to write the d over dx notation first, and then we can move forward from there. Okay, so taking the derivative of the left-hand side, so once we do this, we actually get the, so it's 1 over cosine of x divided by 2 to the power k, multiplied derivative sine of x divided by 2 to the power k, multiplied by that derivative. That's a constant, and well, it's negative sine of x divided by 2 to the power k, and then multiply by the derivative of the inside. I can just factor out the constant itself. Well, really, I'll factor out the negative. So it'll be the negative partial sum k is equal to 0 of 1 divided by 2 to the power k, and then we have a sine over cosine, so I'll just put this as a tangent of x divided by 2 to the power k. Okay, so now taking the derivative of the right hand side, so what we'll get is that natural log of sine of 2x, that's 1 over sine of 2x multiplied by the derivative of this, that's sine of or cosine of 2x, then the derivative of the input, so it's 2, so you write cosine 2x over sine of 2x as cotangent, so we have 2 times cotangent of 2x. Then derivative of this is just a constant, so that's 0, so that just vanishes. Then we have the natural log of sine of 2 divided by, x divided by 2 to the power n. Then once you do this, it's actually basically the same thing as what we did over here, except now it just reverses, so now it's just a cotangent, but now it's actually with the, well, it's still subtraction. So this will be, and then just factor out the derivative of the input, which is 1 over 2 to the power n. 1 divided by 2 to the power n, and then multiplied by cotangent of x divided by 2 to the power n, like so. So now here, let's actually multiply a -1 to both sides, so now everything will change. So we have a positive on the right-hand side, so 2k, then tangent of x divided by 2 to the power k. And then on the right-hand side, everything will, this will be a negative, that will be a positive, so why don't I just rearrange those terms based on the commutativity from there. So we have 1 divided by 2 to the power n, cotangent of x divided by 2 to the power n, then subtract 2 times cotangent of 2x. That's nice. So that's what we have so far. So now next step, let's actually go back to our original problem that was given. Okay, so if I were to go back to the original problem, so let's see, let me write this as original. So if we have the original sum, so k is equal to 2, 1 divided by 2 to the power k minus tangent of pi divided by 2 to the power k. You can actually readjust the index over here. We don't really need to readjust the whole series itself, but we just want it so that these exponents actually match. So what I want is that the exponent to be k minus 2, but to do this, we have to change that, but by doing so, we would have to change the numerator of pi as well. So this to be a k minus 2, in other words, that's the same thing as 2 to the power k multiplied by 2 to the negative square, 1 over 4 on the denominator, but really that just fixes that so that the numerator is just pi divided by 4. So k is equal to, so we still have the same thing, 2 divided by k minus 2, tangent of, so this will be pi over 4, and then 2 to the power k minus 2, just like what we wanted. Now let's actually readjust this back so we have that it's k is equal to 0. So this is actually that easy. to fix. So this is just be k is equal to 0 over here. And that will change that to 1 divided by 2 to the power k, then multiply with tangent of pi over 4, and then divided by 2 to the power k, like so. And here, if we go back to our, well, in other words, we're almost, well, before we get to that now, since there's an infinity, let's actually write that as a terms of a limit, which is what I said earlier that in the video, that we were actually going to get into a limit. So the limit, then we have the limit of the partial sum. We'll just call this, that's n over here, k is equal 0 of 1 divided by 2 to the power k, then tangent, it's just everything on the right hand side right there, pi over 4, then 2 to the power k. This is what we have over here. Now, in other words, since we write that x can be the input of pi over 4, so set x equals pi over 4, in other words, then from there, how about this? Because I said that, let's actually go back to here, draw that arrow. I'll say that this is pi over 4. That's just to denote from over there. And then now we can move on from here. So in other words, I would have to actually, since we're taking this in limits, so that means I would have to take the limit of the right-hand side so that x is equal to pi over 4. So really, okay, the limit as n approaches infinity of 1 divided by 2 to the power n, cotangent of pi over 4 divided by 2 to the power n, then subtract this with 2 times cotangent of, so 2 times pi over 4, 2 pi over 4, so that's pi over, so that's great. And you'll know that, obviously you guys know that the value of cotangent of pi over 2, that's just equal to 0, so this whole term just vanishes. And so what we're left is to evaluate is that we just need to figure out what the limit n approaches infinity of 1 divided by 2n, then cotangent of pi over 4 divided by 2 to the power n is equal to. Right. Okay, so here's actually a little interesting thing that we're actually going to analyze a little bit. So what I'm going to state is the following. So we say that so as tangent of x is equivalent to x, approximately x, I'll say it that way, for some small x, you'll notice that x gets infinitesimally smaller. I'll just write INF for infinitesimally small. Then you'll notice that we can say that tangent of x is equal to x. You can see that if we were to graph tangent of x, then if specifically we're looking at like the domain from between negative pi over 2 to pi over 2, for example, and if you were to take a very small x, like very, very close, so it's like approaching 0 for that sense, you'll notice that as it gets smaller and smaller and smaller, it's actually approaching to whatever your x value approaches. So that's why we can actually state the claim and say that tangent of x is equal to x, right? All right. So from there, we can say that, I can say that this is just the limit n approaches infinity of, so it's 1 over 2 to the power n. Then I'll write cotangent as 1 over tangent. So that means, let me just refix this, the notation over here. So let me first write the denominator 2n, then tangent of pi over 4 divided by 2 to the power n. So the numerator is 1. Okay. Then from there, we could say that, since we said that tangent of x is equal to x for some infinitesimally small x, we can write that as the limit n approaches infinity of 2 to the power n, well, this is the denominator I'm saying, of pi over 4 divided by 2 to the power n, and then numerator is 1. Then you'll notice the 2 over n's cancel each other, so we have 1 over pi over 4. In other words, flip the reciprocal, and there's nothing to plug for n to approach you, so that's just a constant on its own. So really, therefore, we have that our given infinite sum is indeed just equal to 4 divided by pi, like so. And there we have it. The final answer in the red box. It's a lot going on there. I told you we didn't really need to do the same thing from evaluating well, we can really just start from what we evaluated from that past video and then work our way from there. So we saved a ton of work just from that. So yeah, that's pretty cool if you ask me.